Here we are again, rational numbers as exponents. This is actually not new to you. You already know about this. There are two ways for showing radical expressions. One of the ways you've known since elementary school, this way. Let's say this was the cube root. The other way, and we've used this a little bit, is with a rational exponent. Rational because this is a ratio of two integers. We actually got into this because if we wanted to give some instruction to your calculator, for example, if you wanted to find the cube root of 27 on your calculator, you can put in the 27, do the up caret, and then, of course, we have to use parentheses, 1 divided by 3, the 1/3 is there. This isn't new, but we're going to go into it in a little more depth now. You'll be able to write you'll be able to write expressions with rational exponents as radical expressions and vice versa. In other words, you can go from something looking like this to this and vice versa. Simplify expressions containing negative, this is getting interesting, negative rational exponents, and use rational exponents to simplify radical expressions. Well, we did that in the last segment, didn't we? I'm trying to remember what it was. Oh, it was, and put it down here, it was the 8th root of 64. And remember, we rewrote that as 64 to the 1/8. How did this help us? Well, we recognized that 64 to the 1/8, we could take the 64, what was 64? 2 to the what equals 64? Two to the 4th gives me 16. 2 to the 5th gives me 32. So it was 2 to the 6th. So we use that, 2 to the 6th power. And then these exponents, 6, remember we did this, we said, okay, we could look at that as a rational exponent as well, couldn't we? Just say 6/1. We realized that when we have a power of a power, which is what we've got here, you multiply the exponents together, and that would equal, excuse me for this interruption, I need to figure out how to not have that happen. We could multiply these together and we'd have 2 raised to the power of 6/8, which would be 2 to the power of 3/4, which would be, let's see, that's the 4th root of 2 raised to the power of 3. I'm going to go back up here for a minute just to reiterate. This, whatever is in the denominator, is the root, and what is in the numerator, when we're using rational numbers as exponents, What's in the numerator is the power. Okay, I think we're ready to go. Let's take a look at what we'll be doing today. There's quite a bit to get through here. We'll see how far we can get on this session. I might actually break this into 2 sessions. Multiply and simplify. Okay, this is just getting us ready. We're going to distribute we'll have 2 square roots of 13 plus, when I distribute this, it'll be 3. The square root of 13 times the square root of 13, I'm raising, basically, a square root to a power of 2, so that's going to end up being 13. This will equal here we have it. The answer was right there. I'm going to rationalize the denominator. You're familiar with this. We just put together something equivalent to 1, which will do the job for us. We've got it. Okay, rationalize the denominator. This one. Ooh, we need a conjugate here, don't we? We're going to have a 1. Remember, we match this, and we match second. What we don't match is the sign. This one is a sum, so this one needs to be a difference. I'm always going to use the opposite sign. We're trying to rationalize the denominator when you've got a binomial in the denominator. When I work this one out, there. Now, I'm not so sure that that's very obvious. Let me take this aside for a minute, and we'll work it through. Make sure that it comes out that way for us. Okay. My pen back. So when I multiply this out, I'm going to have 5 distributed into that binomial, giving me 5. Okay. 5 minus 5 square roots of 2. And down here what will happen? I'll have 1 times 1 to be 1. I'll have no middle term because of conjugates. I'll have square root of 2 times the square root of 2 giving me the square root of 4, and it's going to be negative. Negative 4. Excuse me, not negative 4. Square root of 2 times square, well, I could say, why don't I? Square root of negative 4. 5 minus 5 square roots of 2 over 1 minus 2, or a negative 1. I've got this negative. I better bring it up. Negative 5 minus, okay, 5 square roots of 2 . So if I take a 5 out of here, negative 5, take a negative 5 out of there, it'll still be negative. It's be 1. Whoops. 1. Yeah, okay. I spent a little more time on that than I intended to, but I think it was probably worth it. I think we're set up properly now to go forward with rational numbers as exponents. Let's try writing an equivalent expression using rational exponents for this. Okay, so we're not going to be using the radical anymore. And we know that we put the power in the numerator, and the power is 5. And in the denominator, we're going to put the root. Okay, so let's try this. Just rewriting this. This would become 64, and my power goes in the numerator, which is 2. My root goes in the denominator, which is 3. I'll try this one. 81. The power of 3, the root of 4. Try this one. Oh, this seems a little more complicated. Let me leave it in its radical form for a minute. I've got 8. Now this power, it distributes to the number and to the variable. Each variable, let's say there's only one. So it's 8 to the 3rd power and x, x to the 6th power. Am I right about that? 3 times 2, yep. Okay, so let's divide this up. I'm going to have the cube root of x to the 3rd power times the cube root, of x to the 6th power, which is equal to, if I put it into rational exponents, I've got 8 as my base. I've got, what is my power? 3 as my power, and 3 as my root. Over here, I've got x as my base. My power is 6, that goes in the numerator, and my root is 3. Well, what do we notice here? I've got basically 8 to the 1st power, x to the 2nd power. But we know when you have something to the first power, you don't bother to write it. So it would simplify to this. I think we can see the usefulness of rational exponents. Okay, we'll go on to the next page. This is just an example. We've got radical notation, looks like this. And the limitation of that is integers. We can only use integers. A 4, a 2, a 3. Rational exponents. Then you can have any rational number. So we remember that a rational number is a ratio of integers. What is this one saying? It's saying we've got 81 to the first power. I didn't write it here, but it's true. 81 to the first power. There's my power. And the fourth root. Okay, let's start with a question here. What is the number whose product with itself is 7? I'd like you to pause for a moment and consider what that would be. Two numbers that, by the way, they're not right. They have to be the same. What's the only thing that's going to work? I hope you took a little time to think about it. The only thing that will actually multiply by itself to give us 7 would be the square root of 7. Well, that's not really true. There is another number I could have used there, right? The negative version of the square root of 7. I could have said negative square root of 7 times negative square root of 7. What is 9 to the 1/2? Well, you could put it in your calculator, right? You could say 9 raised to the power of 1 divided by 2. The parentheses, and you would find that it's equal to 3, which is the square root of 9. So it's just another way of writing square root. Write this without rational exponents. Well, the only way to do it is to use radical notation. 7, we say square root of 7. This one, the cube root of x. This one, the cube root of 8, which we know, of course. Cube root of 8 is 2. Over here, write with rational exponents. We are in radical form, and we want to write it with rational exponents. My base is 11. My power is 1. My root is 3. This one. My base is 3x. Now, here's something to be very careful about. I need to make sure that when I write my rational exponent, it's going to apply to the 3 and the x. If I don't put these parentheses here, it will only apply to the x. So I need the parentheses. The power of 3x was 1. The root 5. Oh, we're speeding right along. I think we might do pretty well here. Go to the next page. What fraction is equivalent to 3 to the negative 1? Remember what we have to do with this? 3 to the negative 1. We think of it as a rational number. The only way to change a negative exponent to a positive is to move it to the other side of the fraction. So this is going to become 1 over 3 to the positive 1. Another question, is 2 to the negative 3 less than 0 because of this negative exponent? Before you answer that question, let's rewrite this 2 to the negative 3 without the negatives. Okay, it simplifies to 1/8. And if we ask ourselves this question now, instead of using this expression, say, is 1/8 less than 0? The answer is so obvious, right? No. Okay, so we're going to rewrite with positive exponents to keep ourselves out of trouble. Because when we see the negative, sometimes, at least early on, it's a little too confusing. Rewrite with positive exponents. So I have to think of this as a rational expression that is being raised to the negative 1/2. That would become 1 over 8 to the 1. Let's see if I can write this small enough. You can do a lot better on a piece of paper than I can do on this. And this one would become 1 over 16 to the 3/4. That's so interesting. Can we work with that one a little bit? 16 to the 3/4. That would be the same as the 4th root of 16 raised to the 3rd power. Now you're going to see in a minute why I'm so interested in this. All we had to do for this was our answer right here. This is all we had to do. I'm just getting carried away. The 4th root of 16, I know what that is. That's why I'm so excited. If I took 2 and raised it to the 4th power, I would have 16. So the 4th root of 16 is 2. So basically what this fraction is I've got 2 raised to the 3rd power. Let me just... This is equal to 1 over 2. This is equivalent to 2 to the 3rd power. What is 2 to the 3rd power? So we can use all of this successfully to simplify things. And up here we are going to simplify. All right, I've got 2, a base of 2. Same base with different exponents. Remember the rule, the exponent rule? It applies here too. That's the same as 2. And what do we do with the exponents? If I had x to the 1st power times x to the 2nd power, you would know what to do with that, right? You'd say x to the power of 1 plus 2, or to the third power. We're going to do the same thing here. We're going to take 4/5. We're going to add 6/5. Okay, if I have, oh, I'm lucky. Same denominator. That's going to be 2 to the, I just add the numerators, right? 2 to the 10/5. Which 10 divided by 5 is 2 squared equals 4. That is beautiful. How about this one? We're going to think about the rules of exponents. Remember when you multiplied, like up here, x to the first power times x to the second power, you were adding the exponents to get to the next stage. In division, if your bases are the same, which they are, then you can subtract what the exponent in the denominator. I'm going to start with the numerator, 5/3, and we're going to subtract 1/3, which will give us, same denominator, not a problem. You don't have to worry about least common. I've already got a common. 4 minus 1/3 is going to give me 3/3 for my exponent. And of course that simplifies to 1. And my answer is simply 5. Aren't these great? Go from this kind of a mess to 4, this kind of a mess to 5. Ooh, but look at this. Power of a power. We know we're going to have to multiply those exponents together. I'm going to multiply them. So I've got 4/3 times 3/8. Now before I do any multiplication of these, 12/24, I suppose I could, because we know 12/24 is 1/2, but there's some other opportunities here. I'm just going to change my pen color for a moment. So 4 and 8 would leave me, once I cancel, 1 and 2, and 3 and 3 would be 1 and 1. So I'm going to end up with a much simpler expression. This is equal to 2 to the 1/2. I hope you like it. I'm actually going to pause now, break it, and you've already had a half an hour of instruction. Let's leave it at that, and we'll pick up the other half hour in our next session. Go ahead and take a look at, we'll be looking at the homework, but we won't go all the way through with it. We'll just do the problems we've learned so far.